This is Cgtn, China Global Television Network.
I'm Shanice O'Mara in London to find out more about brain-computer interfacing.
I'm Guy Henderson in Spain, where decades of engineering norms are being turned upside down to produce renewable energy.
And I'm Emma Keeling, finding out about a group of researchers who are analysing sewage wastewater to predict further outbreaks of COVID-19.
Paralysis is often a result of spinal cord injuries, which prevents messages from the brain being sent to the rest of the body. And in some severe cases, that can be known physical movement from the neck downwards. So I've come to Imperial College London to see how scientists are decoding brain signals, effectively allowing people to control devices with their minds.
At the Brain and Behaviour Lab, they study machine learning systems and biological brains and how they can both learn from one another. Dr. Aldo Faisal heads the research.
Why is this technology so necessary?
It all began with the question that how can we use the power of artificial intelligence to help our biological intelligence if it's affected by disease or injury. And so this brought about the development of brain-computer interfaces that are going beyond what is currently capable by exploiting the power of AI to better understand and automatically understand what the brain is thinking, to translate that into actions for the brain.
The human brain is made up of about 86 billion neurons or nerve cells, which are largely responsible for the way we think, feel, and act. Each connection sends signals or fires at an average frequency of 4 to 10 Hertz, or 4 to 10 times a second. Some even fire at a rate of 3 to 400 Hertz. This is a huge amount of output, so to pick out certain information within a mass of noisy signals is a difficult task.
It's incredibly noisy. To give you a sense, it would be probably like whispering in a typhoon or something like that. It's barely audible, and you're really trying to pick out of these very fast, very noisy signals something.
Artificial intelligence has the ability to sift through all of the data and spot patterns and trends and filter out the noise. But before AI begins spotting patterns and trends, electrical brain signals must be tracked and recorded. That's done using an electroencephalograph, a technique that requires electrodes to be placed all over the scalp. The team working on developing the brain-computer interface technology will be competing at the World Championship of Robotic Systems for People with Disabilities, or Cybathlon. Scientists team up with pilots, people with real disabilities who test and advance their new technology. Pablo Ortega San Miguel is completing his PhD whilst leading the BCI discipline at Imperial College.
Brain-computer interfacing. What exactly is that?
So a brain-computer interface is a device that translates your thoughts, if you want to say, or your brain signals into commands that a computer can use to do something, basically. So for us, you can think of the technology as a complement to our daily life. Like, you could maybe set your alarm using your brain. But I find more meaning for it for people that actually cannot interact with their surroundings.
One of those people is Tom Nabarro. He's been unable to move all 4 limbs since a snowboarding accident in 2007.
So Tom is our pilot for Cybathlon 2020. He's a great person, has a great attitude towards the technology that we're implementing. He's very active. Now, there's an experiment going on, so you want to see it, you can see it for yourself.
I'd love to.
Yeah? Let's go.
Let's go.
So here we are, this is our lab.
Looks awesome in here.
Yeah, technology. Here we have Tom, our pilot,
Hi.
and our team for the Cybathlon 2020.
How do you feel about being part of something so cutting edge and pioneering?
For me, it's been an amazing experience. The event itself is just, it's only just started. There's never been anything really like the Cybathlon. People call it the Cyber Olympics, and it is cutting edge, and it's something that has only just happened because now we're at a stage where there's so much assistive technology. It's becoming such an important part of so many people's lives, and that they're making an event about it.
64 electrodes are being attached to their assigned positions, and it's really important that this is done meticulously and carefully, because this is where all the data is collected. Data about brain signals corresponding to movements, and this is the preparation task.
Each electrode detects the electrical activities of hundreds of neurons that are active or firing in the brain. In between the signals and the electrodes is about 1 centimetre of bone, skin and hair, which make the signals harder to detect. The water-based gel is syringed at the electrode tip to improve the detection of the signals. These signals are picked up by the EEG and then represented as waves on the screens. All this data is stored for the AI to analyse.
As you syringe this very conductive gel
Exactly.
into the connections between the electrodes and your scalp, you're seeing the lights turn green, and that is corresponding to this screen.
The next stage of the process is the calibration of the game that they'll be testing today.
So what exactly are you setting up?
It's the example game, and the idea is that if I'm watching the video of game, I can practice making the signals that I would if I was playing a real game.
What Tom needs to do is repeatedly imagine certain actions so the computer can identify and learn them as being specific instructions for controlling the virtual wheelchair. These imagined actions are known as motor imageries, and the difficulty is in keeping them clear and then repeating them in exactly the same way.
It's quite strenuous. I mean, you just have to repeat an imagery, so you're just trying to think and concentrate. So I try and clench and release one hand as fast as possible, and that sounds strange because I can't actually move the hand, but I can still visualize doing it.
Once this process is complete, the computer is able to create representations of what these imagined actions look like, or which areas of the brain have been active.
So what are these pictures showing us?
So these pictures are showing us Tom attempting to move his left hand and his right hand. And we can see clearly that the power of the brain activity decreases when he's trying to move his left hand on the right hemisphere and the other way around.
The right hemisphere of the brain controls movement on the left side of the body, and the left hemisphere controls the right side of the body, shown here in red as increased and decreased brain activity.
Okay, so these patterns are then fed into an algorithm that will look at those trends.
Yeah, and learn these differences basically.
Tom is now ready to practice playing the game in a dry run. Staying focused on specific thoughts is exhausting, but necessary for providing the AI algorithm with consistently clear signals.
We did not use the data track before, so the model could be unstable. It's fine.
It still needs some fine-tuning, but it's amazing to see him starting to control the virtual wheelchair by thought alone.
And it really is an emphasis on thinking, because with someone like Tom, he can't carry out actions. So it's really about how he thinks that counts.
Correct. We're trying to capture his intentions, and we can capture that through methods called motor imagery, where he imagines that he makes a movement, and say with his toe, and we capture that brain activity. But sometimes it turns out that it's easier to make him imagine other things. For example, thinking about a sound, and that gives you a stronger command.
How soon can we see this technology being used?
Well, the question is ultimately how poor of an interface are you happy with? To give you a sense, so Tom is fully paralyzed, so he's no other way of moving. So accepting that a system such as a state-of-the-art system maybe have just get 1 in 3 or 1 in 2 decisions right is acceptable. But imagine you were to type on a keyboard that gets every second letter wrong. It would not be acceptable. So here it's really where we believe AI can really push it to the next level.
So far, Tom has been using the headset at Imperial once a month. The next step is to use a wireless headset, which can be fitted quickly without much prep work. This would allow people like Tom to provide a lot more data from the comfort of his own home.
So it's tight. Just let me know when there's enough pressure. I'm just gonna do this in some of the electrodes, okay?
It's almost like getting a head massage.
And relax as much as you can. Yeah, so basically these are your alpha waves here.
Wow.
So now you just move your right hand. Yeah, cool. So this is basically what you can see, right? So basically when you're moving your right hand, you have very low power on your left hemisphere, high power in your right hemisphere around these areas. So now if you want, you can try the same, but thinking about doing it. So this is a very weird and alien sensation actually, because not many people actually try to do this in their everyday life. But what you can try and do is kind of try to feel how it feels when you move your hand but without moving it.
Trying to do what Tom did is really difficult, and as you can see, my signals are unclear. To achieve clear signals will take a lot of practice. Feeding the AI with more data to sift through, allowing it to filter the noise and identify the pattern of signals in my thoughts. I must say, continuously imagining an action requires a lot of concentration.
There seems to be so much data here. I mean, how long would I have to be hooked up to this before the machine learns?
So there are two aspects of it, because one thing is how well the artificial intelligence is able to recognize the patterns, and the other one is how well you can generate those patterns.
Hi, how's it going?
Good, I think.
We really believe that the way forward is to let algorithms learn from the data how to best understand the data. That's how we do it ourselves. We learn from experience how to do things better. And that allows us to push the boundaries of what's possible further ahead. The brain is very complex, and we're just really starting to scrape at the edges of what we can start decoding. But already we have made a huge leap forward. You've just put this headset more or less on in just a minute. So we think this will not only make it easier for patients to use it on a daily basis, just pop it on their head, but also it means that we as consumers can benefit on a more sympathetic and in a standard way.
Machines are learning quickly from the way we think, and the technology is advancing rapidly. The challenge is to transfer its use to real-world assisted devices that will improve the lives of people like Tom.
Whether it's about your education, the home you live in, or the items you buy, your money has a story to tell. Because every business story is a human story. Global Business.
November 1940, an historic moment in engineering history. The Tacoma Narrows Bridge disaster in the USA changed the way we think about building large structures. Ever since, engineers have tried to avoid a phenomenon called vortex-induced oscillation, which is what destroyed the bridge. But what if, instead, that oscillation could be harnessed and turned into a source of renewable energy? I'm Guy Henderson in Madrid, Spain, where decades of engineering norms are being turned upside down to create a structure that's designed to shake. Modern life is built around consuming energy, but much of it comes from fossil fuels, and that is unsustainable. Take a short drive outside the capital, and it's clear that wind power is a big part of the solution. Spain is one of Europe's leading producers of wind energy. Burns like these do also have their limitations. You can hear they're pretty noisy for starters. They take up a lot of space, so that means they're not necessarily suitable for densely populated areas. Plus, there's a lot of moving parts, and that means a lot of maintenance. Hello.
Hello.
How are you? Very good to
Welcome.
meet you. David Yanez runs a company called Vortex Bladeless and believes he's found a new way to harness the wind's energy while avoiding these shortfalls. This is called a Vortex Bladeless.
Yes. In fact, we have something like one blade. It's a hollow tube, a vertical mast. We oscillate with the wind with the resonant. When two frequencies, the vortexes and the natural frequency of the structure start to move, we have a way to collect energy from the wind, to transmit energy from the fluid to the structure.
So it oscillates in the wind to create energy.
Exactly.
Is it complicated, or how many moving parts do we have inside?
Yes, we have no moving parts. We have no shafts, gears, bearings. What we have is a carbon fiber rod that absorbs the flexion, and nothing else. What we are trying to do is to develop a new technology, a new tool that maintains similar characteristics than the solar panels. For example, not to produce noise, reduce the visual impact, to avoid maintenance as far as possible.
Jose Vieira is a Vortex engineer back at headquarters in Madrid. So Jose, why are you showing me this ruler?
Well, this is a good way to understand the natural frequency of any structure. This oscillates corresponding to its mechanical characteristics, its length, its strength, and everything. So we base our technology in the natural frequency oscillation of, in our case, a rod of carbon fiber. The easiest way to understand how the vortices are created around, in our case, a cylinder or any bluff body is this, for example, this video. The wind comes in this direction. The wind produces a physical phenomena here in which the pressure is high and low in both sizes alternatively. So at the end, vortices are produced, and these forces produce the movement of the ruler.
Okay, so in an area of low pressure, that would draw the object back towards that area of low pressure.
Okay, yeah, that's correct. If the natural frequency of the device or the ruler and the natural frequency of the vortices are the same, it self-sustains.
Here we have the wind tunnel. You can just see it's completely made from wood.
Prototypes are tested in this wind tunnel downstairs. We've seen the headlines out in the field. What exactly is happening here?
What's happening here is a physical phenomena called vortex shedding or vortex street effect. It's a phenomena that happens when a fluid, in this case the wind, passes through or around a slender structure. It's a phenomena that you can usually see on flaps, on chimneys, also well in aeronautics. It's well known, but everybody is trying to avoid it because it causes some turbulences on the planes, on whatever, and it can make the buildings collapse, like Tacoma Narrows Bridge. Nobody has investigated how to enhance this process or how to absorb the much amounts of energy from the wind in this way.
You really are the pioneers, really, of this. No one else has really been doing anything like
this is state of the art. This is completely new in everything. All the patents are new, all the investigation, all the papers. It's a completely new line of investigation, yeah.
So, inside, the key component,
hollow and it's very, very light.
Very simple science here,
Yeah.
but you have an alternator in here. I know you're a bit sensitive about us getting too close to it because it's prized technology, right?
Yeah.
But what, in very simple terms, what does the alternator do? What's that in there? Why is that
Well,
there?
an alternator, as any other alternator, it converts movement to electricity.
A standard alternator is basically a magnet that rotates inside a coil of copper wire. Movement of the magnetic field relative to the coil generates electricity. So in a car, for example, the engine spins the alternator, generating power to charge batteries and drive the electrics. The vortex alternator is a little different.
In our case, the movement is not a spin, it's like a spherical movement. So we needed to develop a new kind of alternator.
And that's another thing that has not really been done before.
No.
The alternator is driven by a carbon fibre rod inside the cone. Comillas Pontifical University is where these rods are tested. Here scientists test all kinds of material to their limit, including graphene.
This material is made from a liquid polymer, which is a plastic, really. We mix it with graphene, and we have this dispersion of graphene on the polymer. Afterwards, we mix it with carbon fiber, and we end up hardening the material in order to get this plastic composite.
A plastic composite, and the question, of course, is this going to be strong enough for the task of oscillation? The sample is placed into a special machine that stretches it. Graphene can normally withstand such pressure.
You can see the load, the strength.
Okay, so it's pulling it.
We're pulling the sample, so basically what we're checking is how much does the material stand the force we're applying.
But the graphene would stretch a little bit?
The whole material, the polymeric matrix, as well as the fibers, are stretching till some point.
Yeah. Oh!
It did break.
Yes. Did it break? It broke!
It broke.
It's failed! This isn't how it was supposed to go.
Good, we didn't bet.
Wow, there we go. A surprise for us.
Because the fiber is in this direction.
Okay, so it has broken here, there is a crack.
It did,
okay.
yes.
Just in the clamps.
So it is breakable, we've established that, but it's still very strong, right?
It's very strong.
And
yeah.
very,
strong.
Flexible, as in it can survive the oscillation.
It is much more strong than what is needed for the application.
Okay. Your specialty is graphene?
Yeah.
Okay. And how long has this been produced?
10 years or so.
Okay, so it's quite a new material.
It's a new material, yeah, it's a new material.
Okay.
It was actually, a Nobel Prize was won because of the discovery of the material. And so from then till today, they've been trying to use this material in different applications because the material itself has really nice properties for, mechanical and electrical properties that can be used for different applications and for different products.
The hope is to roll out the Vortex bladeless in cities. At less than 3 metres tall, they'd fit on a small roof, even an apartment balcony. The dream, though, is scaling up, so that one day, wind farms like these can be bladeless.
The problem with renewable energy is storing it so that it can be used when the sun isn't shining or the wind isn't blowing. Batteries are expensive, resource-consuming, and currently can't store enough energy. According to London's Imperial College, a cheap virtual battery could be created by hoisting and dropping 12,000-ton weights, that's 1.8 Eiffel Towers, down disused mine shafts. It's called Gravity Energy and is being developed by Gravitricity, an Edinburgh-based startup which hopes to use old mines to make better use of clean electricity at half the cost of lithium-ion batteries. The system stores energy by using electric winches to hoist the weights to the top of the shaft when there is excess renewable energy available, then dropping the weights hundreds of meters down vertical shafts to generate electricity when needed. The scheme is similar to hydropower projects, which use the potential energy of the water stored behind a dam. A full-scale project would drop 24 weights totaling 12,000 tons to a depth of 800 meters to produce enough electricity to power 63,000 homes for more than an hour. By carefully controlling the winches, this period could be extended by allowing the weights to fall at a slower rate and release electricity over a longer period. The company is currently in discussion with mine owners in the UK, Finland, Poland, the Czech Republic and South Africa, where mine shafts can be more than 2,000 meters deep. The Imperial College report said the proposal is the most price-competitive energy storage option because it has a relatively low upfront cost and a potential lifespan of more than 25 years. Gravitricity won't entirely displace all lithium batteries on grids, but it certainly looks like a promising addition to the mix of energy sources needed to lower CO2 emissions.
Earlier in the year, we learnt that analysis of old frozen sewage showed that coronavirus may have been circulating in Europe much earlier than first thought. And now an international collaboration of researchers have moved on from past detection to the present, developing a system of regularly testing wastewater to track the evolution and spread of the pandemic as it happens. Dragan Savic is the director of Sewers for COVID, the group that developed the surveillance system.
We participated in a 48 hours hackathon, and we came with this solution combining sewer surveillance with the informatics side of things, artificial intelligence and machine learning, to link what was found in sewers to what's found in the population so that we can find the best way to early warning system, to how geographically this is developing so that we can find hotspots and where resources should be focused on. There is a bit of a yuck factor with sewers. Only people who work with that get really excited, engineers talking about this type of infrastructure. We humans, ingest food, drinks, everything else, and that is then creates biomarkers that we can then test from the wastewater. And because it collects it from large number of people, it will give us an average picture what is happening. The situation now is we take a sample, we take it to the lab and analyze it, and that can take anything between 2 to 4 hours.
The samples are analysed for the coronavirus's RNA genetic residues, which can be used as a reliable indicator of the level of infection in the area.
This is the technology that will give us, with one measurement, it could do the whole London or large city or portion of a city. So a larger population can be kind of tested in a way so that we can track how the virus is developing in the population.
The data is inputted into software that uses machine learning to calculate infection rates. The software also allows local authorities to input potential mitigation measures, such as isolation for at-risk groups or preparation strategies, which then changes the forecast of potential number of deaths over a given time.
It's multi-purpose, really. It could be an early warning system to tell people prepare, something is happening, but it can also show, when the graph shows the reduction in these traces of RNA in wastewater, then we can decide when to stop the lockdown. And also, how do we prepare? Resources are always limited. So if we know which areas of the city or of the country are in most need for resources, then the decision makers can decide where to send the PPE or even human resource, where the doctors and nurses should be focusing on.
Their prototype proves sewer surveillance could be an effective tool in the fight against COVID-19, and they are now looking into the feasibility of setting up a Europe-wide monitoring system.
This technology can help over time better understand what is happening in the population, because again, testing is very limited and we get just a sample what is happening with the population. With this technology, you get a really good picture of the large population. Sewers are, in that sense, or wastewater is like a mirror of the society.